more people hopping on. All right. Thanks again. My name is Jenna. I work for the Community Energy Association. Thanks for joining us this morning for the second webinar in our Ensuring Quality Heat Pump Installations webinar series. So today we're going to be going through balance point calculations. Just the next slide there, please, Rob. So the Community Energy Association, we acknowledge that we carry out our work on the traditional and ancestral territories of the Indigenous peoples. So through our commitment to truth and reconciliation, we support First Nations, Inuit, and Métis communities in taking climate action and reaching their goals of energy sovereignty, security, and resilience. So I just wanted to start off today's session by acknowledging the Indigenous peoples from all of the diverse and beautiful places we are joining from. So I'm joining from what is now known as Nelson, but for thousands of years has been the traditional homelands of the Snayaks Nation, the Silks Nation, and the Ktunaxa Nation, and is home to the Métis and many diverse Indigenous peoples. So I'd just like to acknowledge with deep respect and gratitude that it is in thanks to their generations of stewardship that we're able to enjoy these mountains, forests, and waters in the way that we do. Just the next slide there, please, Rob. All right, so the Community Energy Association, who are we? In case this is your first time hopping onto a webinar with us, CEA is a registered charity, a nonprofit. We're committed to accelerating bold action by local governments and Indigenous communities related to climate and energy. So we have an unwavering commitment to our clients to provide services and support on the journey from awareness to plans and through to implementation. So we have 49 staff located across 28 communities through 5 provinces and territories. And we bring our collective experience, expertise, commitment to truth and reconciliation, and passion to reduce local greenhouse gas emissions while maximizing co-benefits so that communities are healthy and resilient. Just the following slide. Perfect. So the Kootenay Clean Energy Transition, or KCET, is a project that was developed to address shifts happening in the energy efficiency, renewable energy, and home comfort space. So through KCET, we want to help Kootenay and boundary communities prepare for a more energy efficient and healthy future through training capacity, building sessions like this one. So thanks to the generous support of the organizations you see listed at the bottom of this slide, we're able to offer this workshop for no cost as part of that capacity building piece. We do have a great selection of workshops coming up. As I mentioned, this is just the second in an entire series around quality heat pump installation. So you can find out more details at our website at communityenergy.ca/built environment. I'll also follow up with an email to everyone here today that kind of highlights our upcoming events. And I'll pass things over to Rob. I will say, if you have questions as we go through the presentation, please don't hesitate to ask. I'm monitoring the chat. Feel free to pop them in there. And we'll have time at the end of the presentation for a bit of a Q&A as well. All right, Rob, I'll pass things over to you.
Hey, thanks, Jenna. This session is going to be about balance point calculations. And hopefully by the end of it, you'll understand a few things, what a balance point is, and particularly why it's important. We'll talk about how to find a balance point and how to use the balance point to select equipment. And we'll do a walkthrough of an actual calculation, and then we'll end up with questions and answers. And also, I like the idea of a discussion. So, if you have a question or a comment during the presentation, please don't hesitate to interrupt, and I'd be happy to address a question. So there's 2 types of balance points. One is the thermal balance point, and that is the point at which the outdoor temperature is such that the heat pump itself can't deliver the comfort required inside the home. And so that's when you need to switch to your auxiliary heat. That's a thermal balance point. There's also an economic balance point. It's a lot more complicated because you have to know the cost of energy, different types of energy if you're using a hybrid system, for example, and at what point the switch over to auxiliary is optimized for cost effectiveness. Okay. So balance point is impacted a great deal by outdoor temperature. So you think about it, in the winter, the heat is extracted from outside air, right? So whatever that outside air temperature is going to affect both the capacity and the efficiency of the heat pump. As the outdoor temperature drops, the efficiency and the capacity also drops. Now, it's different for all different kinds of heat pumps and technologies. They're all different in respect to how that outdoor temperature affects them. So first of all, we think about the technology. There's the simple single stage heat pump. Basically, it's on or off. It has the least efficiency. It's probably the least expensive, however. That was the type of heat pump that kind of started the whole thing back in the 70s when I was back then working as an apprentice. That's what we saw. They're still around. They're much better than they were then, but they're still at the low end of the spectrum of technologies. Somewhere along the way, two-stage heat pumps came, and they made a lot of sense because you don't need the full capacity all the time. We spend a lot of time in shoulder seasons. We're not always in the depth of winter. And so that's where two-stage was very effective. It worked at about 65% capacity for 80% of the time, which is a pretty decent representation of how the shoulder seasons work relative to the depth of winter. We thought we had it beat then with the two-stage technology, and then along came variable refrigerant flows, VRFs, or variable refrigerant volumes, VRVs, same thing. And what that does differently than the single stage or the two stage is it ramps up and down based on the load condition. It can sense and measure what's going on in the house and take that compressor outside up or down to match the load requirements. So extremely quiet, extremely efficient. Unlike the single stage and the two stage, it's not on or off. Both of the single stage and two stage, they come on at full capacity all the time in this case of single stage, and a large percentage of the time, or depending on the outdoor conditions with the double stage or two stage. The other thing about variable refrigerant flow is you can do a ratio that's different from single or two-stage heat pump. Those two types of technologies, the single and two-stage, you have an outdoor unit and an indoor unit. That's it. It's a one-to-one ratio. With the variable, you can have one outdoor unit and multiple indoor units. So it's handy in many ways. And then along came, more recently, cold climate heat pumps. If you look at this graph here, you see the blue line representing a standard heat pump, single or two stage. What happens is the outdoor temperature gets colder, its ability to extract heat effectively to the indoor space drops off quite dramatically as a steep curve downward, right? And as you get close to 0 degrees Fahrenheit, you completely lose its capacity to do anything useful. And its efficiency also drops. With the variable refrigerant flows, which is represented here by the green line, you can see that curve is more shallow, and you have more effective capacity for a longer time during the winter. It's not as affected by how cold it is outside to deliver capacity and efficiency. But with the cold climate heat pump, which is a relatively new technology, you can see that red line, it stays at the same capacity and efficiency well into sub-zero temperatures. So what that does is it makes it an effective option wherever we are in Canada, where before in the cold climates of Canada, most regions of Canada, the technology wasn't able to do much for you once you got down to around 0 degrees Fahrenheit to zero to once you got into sub-zero temperatures, you were always on backup heat of some sort. So the game has changed dramatically with cold climate heat pumps. Talk about the importance of balance points. All electric options and hybrid technologies require some sort of calculation up front to know what equipment to use. It's really critical that a balance point calculation is done before you even know what equipment to offer or to put into the project. There's a few systems, for example, in the lower mainland, especially if you put a cold climate heat pump in there, it's not that bad of a climate. And the benefit of that is that you can put a cold climate heat pump in there and require no auxiliary heat. And if that's the case, then you don't need a balance point because it's not switching over anything. It's not going back to emergency heat, backup heat, or auxiliary heat. The reason it's critical to do the balance points are few. The equipment selection, selecting the most appropriate equipment based on performance cannot be done without knowing the balance point. If you don't know the balance point, you don't know how much auxiliary you need. And if you don't know how much auxiliary you need, you do not know how that's going to impact your electrical panel capacity. In a lot of cases, you have a, say you have a 100 amp service, and you, if you're just guessing with the balance point, you might oversize your auxiliary. You might put in maybe 10 kilowatts, and that's going to need 40 amps, and that's going to put you over on your panel capacity. So that's a problem. When if you do the balance point, you might discover you don't need that much. It's really important to know the balance point to discover how much of that panel needs to be upgraded or not, right? Also, cost benefit analysis. If you don't know when your heat pump is switching over at what capacity and what efficiency, you can't do any kind of calculation to discover which is the optimum system to use from an economical point of view. And it's also system optimization. You want the most efficient piece of equipment that you have in your basement or in your mech room to be actually doing the work, as long as it is the most efficient piece of equipment able to do the work. You don't want to switch over to something that's more costly or less efficient before you need to do it. The basic steps to the balance point: load calculations. That's the first step, very important. That allows you to select the heat pump technology. Then you find the performance specs of the proposed heat pumps, the ones that are being under consideration. All manufacturers publish what's called performance curves, basically how the heat pump adapts to outdoor temperature. What capacity at different temperatures and efficiency at different temperatures. So that's the performance specs. And you take those performance specs, plot them on a graph, and where the heat loss line and equipment performance curve intersect, that is your balance point. So let's talk about load calculations first. If you can't do, you have to have a load calculation done to the F280 standard. In other words, you have to have a load calculation to know what size of equipment it's on. Otherwise, you're guessing, and if you guess right, that's a coincidence, and you don't want to depend on coincidence to get the right size of equipment. There is a standard called CSA F280-12. There are several, there's probably like a half a dozen types of software that are authorized and validated by CSA that follow that standard. Any EA, energy advisor, or mechanical contractor has access to these standards and should use them. And that's the first step. Once you've got the load calculations done, then you can select the heat pump technology, whether it's single stage, two stage, variable refrigerant flow, or cold climate. One of the things that we have to straighten out, though, is the language. um, used incorrectly often and creates confusion. So let's just go through it. Industry uses the term supplementary auxiliary heating and backup or emergency heating interchangeably, but on many occasions they are being used incorrectly. So supplemental or auxiliary heat is only that heat that you need to add to your heat pump when your heat pump can't meet the load under winter design conditions. It's the added heat that you need, supplemental or auxiliary. Backup or emergency heat should only come on if there's a failure in your system. It is, as it suggests, it backs up the heat pump, or it is the heat you use in an emergency situation when if your heat pump fails. So when we get that sorted out, we got the load calculation sorted out and the terminology, hopefully, and now we're going to select the heat pump. Um, one of the things that needs to be done first is understand what heat pump you want. Like there's so many out there. You can't just say, I want a heat pump. You have to kind of hone in on what kind of heat pump. What's the technology? Some of that will depend on the budget, right? Some of that will depend on um, green certifications that you need for the jurisdiction that you're in, or for example, net zero, built green, passive, right? There's a few things that'll determine which technology is most appropriate. Obviously, cold climate heat pumps is always the best choice, but it comes with its cost, right? So you have to put that in context of your budget and why you want the heat pump in the first place. But once you do that, then you go into the performance specs of the heat pump, and every brand out there and the different models within those brands all have different performance curves. So it's important to um, uh, find the technology, the brand, and the model, and access the performance curves to find out how that heat pump is going to work in whatever condition you're in. So here you can see I just put a few examples. You know, each of these major brands, and then I could keep going. There's pages and pages of um, major brands and models within those major brands that all have different performance curves. There's no such thing as a universal balance point. So once we find the performance curves, we've done the load calcs, we selected the heat pump technology. We looked at a few heat pumps that we're interested in. That could be based on, what the local supply chain is like and what the local HVAC contractors are used to. Once we do that, we plot the performance curve on a graph. As you can see here, this is for an Armstrong. We plot the heat loss on that same graph, and where that performance curve and heat loss line intersect, that is the balance point. So we can see in this particular situation, using this particular brand and model, that at about 19 degrees Fahrenheit, minus 7.2 Celsius, we no longer have the capacity to heat the inside space. But that is only if the load is greater than that balance point. If the load is lower, for example, you're building a high performance home, then of course that balance point will tell you that you have enough capacity. So the load itself is important to figure out whether that balance point is adequate or not and how much auxiliary you need. So let's take a case. This is a single detached home built in the 80s, 2 stories above crawl, partial basement, about 3,300 square feet. And this is in Kamloops, by the way. It's kind of leaky, 7.5 air changes per hour at 50 pascals. Got our 30 in the attic, our 9 in the walls. They're 2x4 walls. Basement crawl is uninsulated, exposed floor, about 13, R13 and a half. Double pane windows, USI 3.33 or U value of 0.58. The solar heat gain coefficient, which is affecting how much solar gain gets into the building, is 0.4. And 8.7% of the wall area is glass. Okay, so that's the house. And we're calculating this house in 3 stages. As is, that's just, they just want to change the furnace and do nothing else, right? The other one is they want to change the furnace along with some upgrades. They're going to blow in our 60 in the attic, for example, and change those windows to triple pane. And a deep retrofit, which is going to be the same as a light upgrade, except they're going to add R29 to the above grade walls and R29 to the foundation walls. Okay, 3 scenarios to that same house. These are the loads for those 3 scenarios. As is, with no changes to the building itself, this is 95,000 BTU heating load, 34,000 BTU cooling load. If you do the light upgrade, you can see there's a big difference. It goes down to 69,800 and change. And the cooling load also goes down to 28,800. If you did a deep energy upgrade, you only need 30,300 and change to heat that house. So there's a substantial difference, and 20,900 for your cooling load. And you can see why you need to know these numbers, because if you are doing a retrofit, you want to know if there's any plans to do any upgrades to the home, because you don't want to oversize today for a home that's going to change tomorrow, right? It's a big difference. So imagine we're doing the calculation on this. So let's just go one step at a time. The first thing we need to know is, what is the outside design condition? For Kamloops, the design condition in winter is about minus 10 Fahrenheit. The heating load, and then you start at 65 and you draw a line up to the amount of BTUs, in this case, 95,000 BTUs. At 65, you're in an area called stasis. That means you don't need any heat, don't need any cooling. It's kind of in between. So that's why it's the starting point. You can see where 95,000 BTUs is needed at minus 10 degrees Fahrenheit. So you got those 2 things. The next thing you need to know is, what's the performance curve on the heat pump that you're thinking about. So say a standard 5-ton heating heat pump is going to meet your heat loss line at about 32 degrees outside temperature. So obviously that means beyond that, you need a lot more heat. You need some auxiliary. If you put a cold climate heat pump, and I put that there for contrast, that same 5-ton heat pump will give you all the heat you need at a really high efficiency to about 15 degrees Fahrenheit. What that means is that with your standard heat pump, this is how much auxiliary you need from about 32 onward. You need quite a bit of auxiliary heat compared to how much you need for the cold climate heat pump. So you see, it's not just a technology, it's also which heat pump brand and model. They're all different from each other. If you did it, this is with the light building upgrade. So it's really important, because we really want to think about, if you're going to invest money into your house, you want to think about the building itself first, if you can. Now, of course, sometimes you need to change the furnace because the one you have is broken down and it's emergency and you have no plans to do anything in the house. But if you're thinking about the house improving your total energy performance for whatever reason, lower your carbon footprint, lessen your weekly monthly utility bills, or just improve the quality of comfort in the house, whatever the reasons, we want to know that up front. We don't want to just change out your furnace if you plan to put some insulation in the attic, add better windows and so forth, right? You want to size for the actual condition under consideration of the house. If you go to a light retrofit, you can see here, we're still using the 5-ton heat pump, right? Uh, Here we go. But we need a lot less auxiliary heat. So this is with the light upgrade, and let's go back and see what the difference is. This is with the as is light upgrade. You see that heat loss curve went down, and therefore the amount of auxiliary also went down. But likewise, the amount of auxiliary required with the cold climate heat pump is less than 10,000 BTUs. It's about 3 kilowatts. That went down quite a bit as well, which makes a difference because now you don't need as much capacity on that panel. Your need to upgrade that panel is reduced or doesn't exist. You might be able to get away with the same size panel you already have. If you're planning to do a deep upgrade, oh, wait a minute. This is the deep energy building upgrade. Now you can see what happens here. Not only do you need less energy to stay comfortable, um, you can go down to a different size heat pump. Your upfront costs, in other words, for heating and cooling your home has gone down quite a bit for a couple of reasons. You don't need as big of a heat pump, for one thing, and the amount of energy that heat pump has to deliver to keep you comfortable is very little. So it's one of the benefits of a deep retrofit upgrade to the home. You can see here that with the cold climate heat pump, in that case, you don't need any auxiliary heat at all. The balance point is at the line, that vertical line, which is your design condition. It can meet the design condition without any auxiliary heat. The question comes up often is, now what I've just showed you is all about the thermal balance point, right? That's where you discover the ability of the heat pump to deliver comfort in your home during the winter, whether it can do it throughout the winter or if it needs to be supplemented at some point during the winter. That's the thermal balance point. The economic balance point is a whole different thing. It's about the comparing the energy cost for example, if you have gas backup versus electric backup, how much of that backup there is and how much you need and when it should come on to not only keep you comfortable, but to save you a few dollars, right? That is a complicated set of equations. And rarely is it effective in our province because of our cost of energy is not so out of relation to each other as it is in other jurisdictions. In other words, cost of gas, the cost of electricity, and the cost of electricity at different efficiencies of heat pumps is not that substantial. I want to look at, to provide some context for costs. I want to look at this house here. We did this set of calculations in Vancouver. It doesn't matter. These same principles apply no matter where this house lives. And it's just the cost under design conditions. So it's the design condition, coldest days of the winter, for each hour, based on the heat loss of this house, how much is it going to cost? So here's the numbers here. So if you just had natural gas, boiler or furnace, As is, each hour would be $1.24. Light retrofit would be 94 cents. If you did the deep retrofit, it's down to 41 cents for each hour, right? If we were to switch that house to just electric, straight head electric, like baseboards, for example, it goes up quite a bit, doesn't it? It's $2.17 for as is, what, $1.64 with a light retrofit, and 72 cents for a deep retrofit. And that's thinking of electricity at an efficiency of 100%. The way that's calculated is 1 kilowatt of heat going in gives you 1 kilowatt of electricity going into that baseboard gives you 1 kilowatt of heat. It's 100%. Whereas the gas boiler, even the most efficient gas boilers or furnaces, is a little less. The more efficient ones that are down around 95, 96% for the best. If you go to a standard heat pump, nothing special, just a two-stage heat pump, for example, you're going to get efficiency, which is measured in coefficient of performance, but who cares? What matters is it's over 100% efficient. Relative to straight electricity, that COP of 2.0 is 200%. You just think of it as a percentage over electricity. Right now we're at $1.08 for that hour, right? We're actually less than the cost of gas, and so on. If we go to the light retrofit, it gets lower and lower. If we go to the higher quality heat pumps, the VRVs, where we're typically looking at a 2.5 COP, 250% efficient, the price is even less. That's 87 cents for that same hour, and so on. If you go to the very best products out there in the market, that would be a cold climate heat pump, for example, or geothermal systems. They'll be in the ballpark of 72 cents for that same first hour. So you can see when you start thinking about these numbers, how it can get very complicated to do a cost benefit analysis, enough to find out where your economic balance point is. It is almost always the case that your thermal balance point is your best place for your auxiliary heat if you have to have it to take over. So just to recap what we just saw on the last page, we only need a COP of 1.75, 175% efficient, to equal the cost of natural gas. 1.75 a COP heat pump is nothing special. They're pretty standard off-the-shelf heat pumps. You can get them anywhere. In the example shown, the heat pump would be equal to natural gas and operating costs at an efficiency of 1.75. So it is pretty easy to get there. So in almost all cases, the thermal balance point is going to trump what the economic balance point says anyways. So understanding the balance point of heat pumps is critical for what? First of all, choosing which technology and brand of equipment is most suitable for your project. You need to do it. Choosing which type of auxiliary system is most appropriate, all electric or hybrid, for example, you don't know unless you do a balance point calculation. Knowing what to expect from an operating cost perspective, there's no way to know that unless you do a balance point calculation. And optimizing the system performance, knowing when the best time for that heat pump to either be assisted by electric strips, your auxiliary heat, or switch over to your fossil fuel, your gas furnace or boiler, right? None of that is known. You can only guess otherwise, unless you do a balance point calculation. Calculating the balance point begins with a well-executed and compliant set of load calculations, right? One standard of practice forces another standard of practice. Doing your load calculations is just not good practice. So you have to have those load calculations anyways in any kind of retrofit or new construction installation. Use the equipment performance specifications to plot the capacity and efficiency at varying outdoor temperatures. An economic balance point is a complex calculation which should occur at whatever temperature the capacity of the heat pump is no longer able to deliver the heat pump or the heat, sorry, required to meet the load. I think that's it for the information on balance points. I believe everybody's getting a copy of this. Is that right, Jenna?
Yes.
Yeah,
Yep.
yeah. And so there's some other good sources here that you can go to for really good information. Natural Resources Canada, Northeast Energy Efficiency Partnership, AHRI, that's a third-party testing agency. All equipment is tested. By AHRI. That's where you find the performance um, um, capabilities of the equipment. And a nice thing, it's not the manufacturer's hype, it's third-party testing, right? And also the Home Performance Stakeholder Council has some really good information on heat pump best practices and installation guide for existing homes. And that's it.
Great. Thanks so much, Rob. I really appreciate it. We do have lots of time left for questions here. So we've had some come through the chat. We'll start with those. And then folks on the call, if you have any questions, feel free to continue populating them in the chat, or you can raise your hand as well. And I'll just let you know, as we do go through these questions, there will be a point where you'll see a poll pop up. It's just a feedback poll. We really do take into consideration everything that we hear from you folks as we plan out future kind of training, workshops, information sessions, etc. So please just take a couple minutes to let us know what you thought. Okay, so our first question here, we're starting with Bruce. Hi, Bruce. Thanks for joining us. It's nice to see you here. Bruce asks, what do you think of a separate ductless cold climate heat pump for auxiliary heating? Unit sits dormant until needed at extreme outdoor temperatures.
Separate ductless heat pump as your auxiliary heat. Auxiliary to what?
Bruce, you can go ahead and respond in the chat or unmute yourself.
Oh, yeah. Hi, Rob. I'm just thinking that when you hit that balance point for your main heat pump, rather than switching over to resistance heating, which is expensive, can we use a separate heat pump that's completely separate from your main heat pump to kick in instead of the resistance, which should be still at a COP of 1.5 or 2 or 2.5 at minus 25?
Yeah.
It just seems to be a cheaper way to have auxiliary heat.
Okay. There's a couple of points that need to be addressed in that potential scenario. One is if your main heat pump is unable to manage at sub-zero temperatures your heating load, right? The chances are another heat pump won't be able to do that. Also, unless you're mixing technologies. So maybe you have a standard single or two-stage heat pump and it kicks out at, whatever, 0 degrees Fahrenheit. Then potentially you could go to a better technology heat pump, like a cold climate, to do the auxiliary. But then the question becomes, why not just get the heat, that cold climate heat pump in the first place? So you're not, then in that case you don't need an auxiliary heat pump or an auxiliary heat of any kind. So if a heat pump can do the auxiliary heat, and uh, it should be able to do your main heat as well. Does that make sense?
Sort of. It's just that if I have to design a heat pump to cover all of my heating loads, I need a large heat pump. And I'd rather operate on a more efficient, smaller heat pump and then add auxiliary later. That's just my idea anyway.
Yeah, well, I mean, at the end, if you're using heat pumps, period, right? You've got to heat that whole building um, at the design condition, right? And
Right.
so you need a heat pump that can meet the design condition, whether that's your main heat pump or your auxiliary heat pump. That becomes the question, the cost benefit of that mixing one technology with another technology becomes a question. But just imagine if your main heat pump kicks out and you've got a different heat pump to do the auxiliary, that's got to do the whole house too. So the question is, why not have that technology doing the whole house in the first place?
Right. Yeah, I'm just thinking design temperature only covers 98% of the events though, right? So we still need to look after that other 2% somehow.
Right. And if it's then if it's only 2%, it is, in most cases, it's a little more than 2%. But if it's a small percentage of the total, then what you want is something that has the least cost amount, upfront capital cost to put in there, because you're even if it's less efficient, like electric strip, it's for such a short time that it doesn't warrant too high of upfront capital cost, right? And if you're saving on your capital costs, then it's okay for it to be working at 100 instead of 200% efficient if it's just for a short period of time.
Yep, totally agree with that for sure.
Great, thanks, Bruce. Our next question here just says, I've heard from contractors that the average COP for the heating season is about 3. Is that a good rule of thumb?
No, it's not. It depends on the technology. And the COP is a snapshot, right? Your overall efficiency throughout the winter is a blend of those snapshots. Um, a good heat pump COP will be 3, but that's the elite brands, the elite technology. Typical over the winter, it's going to be somewhere between zero point 0.2 or 2 and 2.5 is more the average. Now there's heat pumps out there, single stage ones, the economy models that are less than that, right? They're usually for market built homes, spec homes, that kind of stuff. But the majority, the bulk of heat pumps are in the range of 2 to 2.5. Then that is blended throughout the whole winter.
Great, thank you. And then our next question, while doing the balance point analysis, should I look at the COP or the SCOP?
The COP, and COP is the simplest. It is a simple conversion of kilowatts in versus kilowatts out of heat.
Great. And then our next question here, can we use actual data to determine load? If a gas furnace, can we deduct estimate of gas hot water to determine actual gigajoule load? A couple of years of data.
You could on an existing home, you have a huge benefit because you can see what the amount of energy consumed was, and as suggested, that the only complication to that is you have to take out what's not space heating, that's using gas, for example, right? So your domestic water, right? So you have to somehow isolate the domestic water from that equation to get a fair idea of what was actually consumed for specifically space heating over that time.
Great, thank you. And Jeanette just said she had a question but wasn't able to raise her hand. Jeanette, do you want to unmute yourself there?
Sure. A couple of questions. I'll just start with one. So a lot of people, when they're looking at doing retrofits, they might have limited finances, and so they might choose to do the retrofits in stages, often prioritizing heat pumps first, partly because they want to reduce their electrical bills and or they want the cooling. So, do you have any advice for people, or what can I help people understand they're going to get a heat pump that's sized to the current condition of their home with retrofits to be determined. It sounds like it could make a radical difference if they end up adding a ton of insulation or really good windows. How do you navigate that? Or suggestions for them?
It is a really good question, and it's not easy. So part of it, um, if it were me, if I were in your house, I would want to know what you have in mind, and that would help quite a bit. So if you're thinking this year, I'm just going to blow in insulation in the attic, but a few years from now, we're going to really make changes, could change all the windows, put more insulation here and there, and tighten the house up so it's less leaky, right? Um, that would at least give me a little bit of a red flag that I would put my mind to. And in that case, my default would be to go to variable speed, which has quite a range of capacity, right? So now it might work fine at a higher capacity, but it has the ability to modulate down when those retrofit improvements to the building occur. That would be probably my first instinct, is to go to a variable refrigerant flow type of technology. And what I would do is probably want to put electrical supplemental heat in now while the load is at its highest, that can just simply be disconnected down the road when the load is a lot lower. It's because the cost of electric strip is not that much in the scheme of things, like a couple $100. So it's not a big deal to disconnect that later on down the road when you don't need it anymore. So that's kind of how I would approach it.
Yeah, that's great. That's helpful. And do you have I'm looking at the different technology options, a single, double,
Mm-hmm.
variable, whole climate. Um, I'm wondering how much they vary in price, and if there is, like, if all things being equal, let's say price wasn't an issue, would it always be good to go for a cold climate? Like, are there better technologies like the variable that might have more flexibility? What, yeah, two questions there, really.
Good questions. Yeah. So there is quite a price difference. There's even within the same technologies, the price difference is based on brands. Where was it manufactured? Whether was it manufactured in China or Indiana? Will make a huge difference. Is it Canadian or not? Makes a huge difference. Even though it's the same technology. The but I mean, budget is everything, and if I'm thinking about replacing my HVAC equipment, if it's an emergency and I didn't have the money, put in the bank and saved up for it, I'd probably go for I'd I'd try to get in on variable refrigerant flow, although I would go for probably something from China because it's less expensive. If that's my only option compared to not having a replaced heating system. But if I'm thinking big picture, I want to just reduce my carbon footprint, and I want to reduce my energy consumption, and I want to fix the house up, at least fix some of the leaks and make it less leaky, drafty, and that kind of stuff. I would definitely go to better quality heat pump, something that's like a brand like the Japanese brands Daikin and Mitsubishi, or some of the North American major brands, and they would be pretty comparable in price when you get to the higher quality products within each brand's catalog. Um, the cold climate heat pump is a variable refrigerant flow heat pump. Living in the lower mainland, I might not need a cold climate heat pump to do the work. And so why spend the extra money? Because there's a premium involved in getting a cold climate heat pump. But if I'm outside of the lower mainland, or climate zone 4 and climate zone 5, especially 6 or worse, then I would not hesitate to get a cold climate heat pump. That would be my first choice. And I think that down the road, you're probably not even going to see the single stage heat pumps anymore. You might see the two stage, right? But I think cold climate technology will take over because there's not a lot to it. The add on to the VRV and VRF systems is not much. Yeah, it's just a vapor injection cycle in the refrigerant. And so pretty soon there's going to be a lot of copycats of that technology and variations of it, to the point where I think cold climate heat pumps will be just become the pretty ubiquitous in the industry.
Thank you.
Great. Thanks, Jeanette. And just going back to that first question there about doing multiple retrofits, I know, Rob, just through other presentations with you, that there's opportunities when doing the load calculation to take, if you know that the insulation you're going to install or the new windows, that you can include that in your load calculation, right?
To include which? Say that again. To
Like
include?
planned retrofits to the home. So
Yeah, yeah.
adjust kind of in the you can adjust for the windows that you're going to
Oh
install,
yeah,
for
yeah,
example.
yeah, yeah. Oh yeah, yeah, yeah. I mean, if you know ahead of time that there is a potential that, a reasonable expectation that the elements of the building are going to change, you can do the iterations on the load calcs very easily. It's just a few keystrokes. Change all the windows of this, change the walls of that. Once you input all the other stuff, then the actual iterations, there's nothing to it. That's the fun part, is to see what happens if you did this, did that, right? So that'll change the load, that'll change the equipment choices, it'll change your upfront costs, your operating costs, changes everything. And that helps determine, how far to go with the building itself. We have to keep in mind that, the more work you do to the building, the better off you are. That's a passive thing. Once you put the triple pane windows in there, you don't have to maintain them every year. You don't have to oil them. You don't have to do anything, right? Um, and it reduces the size, therefore your capital costs of the heating equipment, right? So it saves you money on that part as well. And your windows have a long life cycle. You don't have to replace it every 15 years or 20 years. And that's assuming that it's a well-maintained mechanical system. You have to maintain it, and eventually the technology will either be eclipsed by new technology, or the heat pump will get old and tired and quit on you, and you have to replace it. 15, 20 years, probably in that ballpark.
Right, thank you. All right, I'll move along with the questions in the chat. Bruce, I do see your hand up there. I'll slot you in just after these few questions here. So Greg asks, I find it hard to get the heat pump efficiency curve off the net. Is there a good site to find this? We know there's a list of heat pumps available for grants.
Yeah, there's two places to go. One is AHRI, right? That'll give you the performance at different climate conditions, different temperatures, outdoor temperatures, right? Just snapshots. Um, It'll tell you whether it can deliver capacity at all in the sub-zero temperatures, but even if it can, it'll tell you what that capacity is and what its efficiency. And again, the beauty of it is third-party rating, AHRI. They have basically a directory. You just find the product, and it'll give you its third-party rating. The other place is the manufacturers themselves. That's what we do. We go to the manufacturer sites, we look up the model, and we go into the technical specifications. And there's either a curve on a graph to look at, or there's a math equation to use, which gives you the ability to put it on a graph. So those are the places that we go to get those performance specifications.
Great, thank you. Okay, we just have a couple of comments here. Excellent presentation. Our next comment was, I was involved with getting a grant for a customer who got a Dicon heat pump installed. It's set to run down to -18 Celsius, and then it kicks over to propane, so no natural gas is available. This is north of Cranbrook. It only kicked into the propane mode for 11 days this year. Great.
Right, so it did what was expected, It managed to deliver the comfort during sub-zero temperatures, except for 16 days, right?
11 days. Yeah. Yeah.
11 days, 11 days.
Mm-hmm.
Well, that's a good thing. That's good. And I'm assuming, I mean, was it all 24 hours of each of those 11 days or parts of those 11 days? Because that makes a difference too.
Right.
That would typically, the run would be in the early morning
Mm-hmm.
when it was below -18, and then the temperature would rise during the day and the heat pump would kick back in.
Right on. Okay. Yeah. So that's good. So the performance is doing what it says it can do. And that's what we found. We actually found, I find this very unusual because I'm used to hype from manufacturers and product suppliers. But in the case of cold climate heat pumps with the Mitsubishi and Daikin, Arctic, there's a few of them out there. We've had these things installed in very cold climates in BC for many years now. And we've had the luxury of being involved in some of those cases with governments and utilities where they've data logged the performance over the seasons. And so now there's a few seasons of data that we can look at. And what is surprising is that in all these cases, that cold climate heat pumps actually outperform what they say they can do, which is kind of is different than most products, and it's kind of nice. So they tend to work better in cold climates than their third-party ratings say they do. And the amount of auxiliary or backup heat that comes on is less than we predicted. So that's the good thing about cold climate heat pumps.
Yeah, great. Thank you. Rob has to hop off right at 9 o'clock. So we have a couple more questions here we'll try to get through. And if we don't get through them all, I can follow up with everyone via email as well. Billy asks, how much do forecasted changes to average regional temperatures factor into these calculations, if at all? Will average heating and cooling loads change over the next couple of decades?
That's a really good question. We don't know, but if we consider previous trends to now, to date, what we can know is that we have more extremes. What we do also know, and it's kind of a paradox, is the winters are warmer. We get summers are hotter. And imagine, somebody like me who's been looking at weather data for all his life, for forever. That's because every system we design and work with, we have to know these things, and you can't help but notice that over the years, the temperatures have gotten hotter in the summer and warmer in the winter, with that paradox of exceptions where you get an extreme cold event that never used to happen as much, or an extreme heat event that never used to happen as much. So it's a good question, but I can tell you this: we are required to use the climatic information provided by the BC Building Code in BC, and we do use it. But what we do internally in our particular business is say, yeah, okay, we're going to use that design condition, but we're going to actually input a colder winter and a hotter summer, just to provide resilience into the system that we design. And I think that's a wise thing to do.
Great. Thanks, Rob. Bruce, I saw you put your hand down. Do you have a quick question we can answer in the last minute or two?
It's not that quick. That's why I put my hand up. Maybe just give it a try here. So I had a client who did his own research, tried to size his heat pump and choose it. First, he has a 90s house with a perfectly good distribution system, went with a mini split because he thought it was more efficient. And second, he went to the NEAP site and found a heat pump that had a really low end BTU and a really low capacity factor at the high end. But it was a 4-ton heat pump when he might have been able to go with the 2-ton in that house. you think about those things as far as is it, this thing at a coefficient of performance? It said 7 on the NEAP site. So there's a few things just thrown out there for you to comment on.
Yeah. Okay. So the NEAP site is a relatively new organization that is it. If you, let me put it this way: if you have a COP of 7, that COP of 7 is only going to occur if for some reason you want heat on a hottest day in the summer, because otherwise it's impossible to have a COP of 7. Right? It just, there's nothing out there that exists that can do that in a single phase residential market. Right. So that's the first red flag for me is, okay, something's wrong here. That 7 doesn't exist in reality. Right. So what is it is then the next question. Well, what's really going on here? What is the actual COP? Who measured it? What third party measured it? How was it rated? How was that rating verified? Because everything you just told me means that there's some critical missing information here. And the information that there um, has been either misinterpreted or miscommunicated, or is just simply not real.
Okay, great. And it is time. So sorry, Bruce. I don't. You're right. That wasn't that wasn't a quick question to finish this off. But folks, I'm going to keep this room running. If you do have questions that you didn't have a chance to ask, pop them into the chat, and I'll follow up with Rob another time. Thanks so much, Rob, for joining us today, and thanks everyone who signed on. Our next webinar in this series is around quality attributes of a heat pump installation on March 27th. So keep an eye out on your email for the registration link there.
Okay, thanks, Jenna. Thanks, everybody. Thanks for the opportunity. Really appreciate it. Take care.
Take care.
Bye-bye.